Chapter 5, Part 3, how does light tell us the speed of distance object? So if I have a stationary train, let's say, okay, and I have two observers, one on the right-hand side, the other on the left-hand side, and they will hear the train just, there's no difference between left and right, right? Because the train is a stationary. However, if the train starts to move to the right-hand side, then the frequency of a light, okay, is getting compressed compared to the left hand side. So if it's moving to the right, we call it that one of them is blue shifted, the other one is red shifted. When you have an observer here, okay, and the object is moving away from that observer, the spectra is red shifted, meaning that the spectra will shift towards the red part of the spectrum. However, if this for this object, or for this object being seen by this observer, the spectra is blue shifted, meaning that the object is moving, the spectra is moving to the blue. It's the same for sound, it's also the same for light. So when we're looking at a faraway galaxy, and this is what Hubble did, when he was looking at the faraway galaxy, notice that all of these spectra that he's looking from these galaxies are all redshifted, meaning that this object, whatever it is moving away because it's red. So this, and this is exactly how he found that these objects are moving and the universe is expanding. So I put these on Canvas for you guys, so you can download them. And so this needs to be played on your computer, so you can hear what a Doppler effect look like for a car passing by. So we can't really play it here, but I can play these two for you, so you can kind of have the same idea of what I'm talking about, specifically this one. So if I have a laser beam pointing toward a specific direction, if the if the laser is stationary, it's producing the light in a specific wavelength. However, if it's moving towards the observer will hear something completely different. Let's take a look. So I here have a laser beam, and it is a stationary, right? So it's producing the beam, it's producing the light, but they are consistent with one another. However, if it starts to move, then you can see that these wavelengths are getting compressed. They're getting closer to one another, right? So, um, so you can also change the velocity here of the helicopter very low, so you can kind of see what I'm talking about. Backwards, very high velocity towards. So we can play with these and kind of get yourself familiar with. It's the same for spectra when we're looking at the spectra. So we compare things with our stationary in the lab. So this is the stationary spectra that we get from the lab. One object looks like this. So that means that object is moving away from us because all of the spectra is shifted towards red. So this is shifted toward red, this has been shifted toward red, this has been shifted towards red. So all of them have been shifted towards the red part of the spectrum. If it's going even faster, you can see the shift is even more, and it's more pronounced, and it's more, you can kind of see it. If it's moving towards you, then it will be a different story, because then the spectra will be blue shifted. All of these three lines, they're moving to the blue part of the spectrum. If it's even moving faster, see, the shift is more pronounced. Okay? And it's only working for radial. In other words, it's only working for radial component of velocity, meaning that if object is moving perpendicular with respect to you, with an angle of 90 degrees, you don't see any shift. You only see shift if it is moving either away from you or if it's moving towards you. That's when you can see the shift happening. So red shifted, moving away, blue shifted, moving towards you. If it's moving somehow like this, in this direction, you can divide its velocity into two components, one in the radial direction, the other one perpendicular to. And so radial will give you enough information so you can identify the velocity of this object, but you don't see any shift for vertical, okay? So because it has an angle of 90 degrees. Thought question. Again, pause the video, read the thought question, try to answer it, and then come play the video again, okay? I measure a line in a lab at 500.7 nanometers. The same line in a star has wavelength of 502, so it's a little bit more, 502.8 nanometers. What can I say about this star? A is it is moving away from me. B, it's moving towards me. C, it is unusually along a spectral line. No, C is incorrect. But what is it moving away from me or is it moving towards me? So the key is this. The stationary line that I measure in the lab is 500.7 nanometers. It is now 502.8. So it has moved, but has it moved towards the blue or has it moved toward the red? So it has moved towards the red portion of the spectra, right, which is at 700 nanometers. So it is moving away from me. Okay, so we can measure these red shift and blue shift in the lab, and I'm gonna play this here, but they're again also available for you. You can play with them, download them on your computer. They're available, and they won't harm your computer at all. So here is spectra of a stationary hydrogen gas in the laboratory on top, and spectrum of a moving cloud of hydrogen in the sky somewhere between galaxies. So here you can change the velocity of it to either moving away from us, so red shifted. See, it's not exactly here anymore. It's been moved towards the red. Or you can say it's moving towards us, so it is blue shifted. It's moved towards the blue part of the spectrum. And the same is true here. So I have a star, but I have a hydrogen gas blocking some of its light. So that's why there is these absorption features here. And it's towards the Earth. So now I can play with its absorption feature. Is it moving away from me or is it moving towards me? Then I can kind of see that, let's say this scenario, with a speed of 19,750 kilometers per second, that object is moving away from us because the spectra is shifted towards the red part of the spectrum. Okay? And you can kind of guess the velocity of that cloud. For example, if you have a line here, okay, let's say that this is my line. I can identify my line here. And then let's say that I want this line to be shifted here instead. So then it can give me that the wavelength shift is this much and the relative velocity is this much. Okay. Let's say that I have a line here, but I want to see, I have seen the line here, for example. That line in the stationary is being seen here. I want to see what I have. So the shift in the wavelength, which is negative, so it means it's going to blue, and it's also relative velocity of this much. So you can really play with these and make yourself familiar with the concept of red shift and blue shift. So we're going to talk about the telescope and what we're really dealing with here. We like the telescope as big as they can be. So telescope collect more light than your eyes. So they have a bigger light collecting areas. Okay, and the telescope can also see more detail. So they have more angular and resolving power. They have better resolution than your eyes, right? So for example, just give you an example of these two. So when we say the bigger the better, that's what we're talking about. This is the Keck 1 and 2. I use these telescope a lot. So the larger light collecting area, and so a better angular resolution. That's that sort of thing. So here is just to give you an example. These are the mirrors of Keck. Okay, so this is the size of a human compared to the mirrors of a Keck telescope, and this is only the mirrors of the Keck telescope, which is right there. So let's talk about the bigger the better scenario here. And so let me go ahead and play the light collecting area refractor here. All right, light collecting area. Here we go. So here's a telescope, and you have a diameter of the telescope of 0.1 meters, okay? If I increase the diameter, I am getting more and more light as I am doing so. What effect does it have? If you're doing that, not only you're getting more light and information about whatever object that you're looking, but you're getting more and more resolution because you're collecting more light of a specific sample. Okay, so that's one of them. The other one is the angular resolution. So here would be a very good example of what we're talking about. If you're looking at this light right there, you really don't know if this is a one source of light or is it the two separate sources of lights, because you do not have angular resolution to resolve this. Your eyes cannot understand that. Okay, I always give this example to my students where let's say that you're standing on top of arch and you're holding two candles, okay, one on your left hand, the other one on your right hand. Someone is standing in Washington, D.C. and looking at the arch, for example, and there's nothing else in the universe, cannot resolve and doesn't have enough resolution to say that these are one source of light or two sources of lights. So let's see. Unless you are very close or you're using a telescope, that you can say, okay, now this was two sources of different lights. So kind of like that. And so the next one I wanted to show you the telescope. So the mirror size. Okay, let's see if I can find it. Mirror size, there it is. So here, you can see that I have a telescope here, and I'm looking at a binary star, double star here, but I can really see it because I don't have enough resolution. The telescope diameter that I'm using is only 0.1 meters, right? With an angular resolution of 1.25 arc seconds. Now, if I increase this, at some point you can identify, oh, maybe there are actually two stars here with less than 1 meter air telescope. So if you go even all the way to some big like 10-meter telescope like Keck, then you can easily see that there are two. But not only that, you can actually see them perfectly well. Okay, so the basic of a telescope, you have refractor or refracting telescope. So which is basically the light gets in and it's getting refracted through a lens and then going through an eyepiece and focus point, and you're looking at the focus point. But most of the research telescopes are designed in a different way. They are reflecting. So it's a combination of a mirror and a lens. So here you have a primary mirror, and that's where the sun, where the light is hitting, getting reflected. And then you have a secondary mirror, which reflect the lights for you the second time. So almost all of the research telescopes are reflecting. So this is Gemini North 8 meters telescope. Again, we really, these are mostly, most of these research telescopes, what you can see on background is right there is Subaru, but we're really interested to see, to get more and more light. So we have built, and this is in Hawaii. So there is a particular reason that we build these telescopes on top of mountains, because we want to avoid, um, light pollution and a lot of clouds that are blocking our way. So this is above the cloud level, as you can see here. So there's the iShell spectrographs mounted in NASA IRTF, NASA Infrared Telescope Facility. We use this a lot here at UMSL. And it's a great telescope. You can also guide on objects with this telescope during the day, meaning that the telescope can track the object during the day. So we can do daytime observations of these objects in the night sky or in the sky. And you're all here, the Mauna Kea, Hawaii. So if you ever go to Hawaii, I highly encourage you to go to the Big Island. And once you go to the Big Island, I highly encourage you to go and visit the Mauna Kea. It's fantastic. It's very awesome and nice to see all of these. So we generally, make different designs for a telescope for different purposes. So different designs because we care about different parts of the wavelength. So for example, this is a radio telescope in Puerto Rico, but unfortunately it collapsed, just not usable anymore. But the point is, even if this is not a clean surface, it will still be very good to reflect the radio wavelength for us. So that's what we care. That's how they designed this telescope. That's why they designed this telescope for. But unfortunately, it's just not working anymore. So we have X-ray telescopes, and they use specific optics. So the first set of nested mirror deflects X-ray to the second set, and the second set will have it directed to the focus points. And these are very, very powerful telescopes that we use, that we can observe with X-ray. So why do we put telescope in space again? If we can put them in space, there are different reasons for it. And it's not because they're closer to the sun. They're just few meters above our atmosphere, a few kilometers above our atmosphere. Okay, so and they're not really close, because compared to this distance between sun and Earth and the rest of the solar system, a few kilometers is nothing. Okay, so we primarily put them there because of the light pollution. There's a huge light pollution that we have on Earth, which doesn't let us to do our job the best. So that's what we do. Second thing is the turbulence in our atmosphere. If you're not having the atmosphere, then you don't have to be worried about the atmosphere blocking your view. Also, atmosphere absorb most of the electromagnetic spectrum, including UV and X-ray and most of the infrared. So, so it's very, very good that we can send some of these telescopes to the space, so we can study them. The visible part, which Hubble works, and the radio wavelength, you're perfectly fine to do it on the ground, but in order to do it an infrared and near infrared, you have to be sufficiently away from the surface of the Earth. If you wanted to do an X-ray or gamma ray, you have to be way above the ground. So that's why we're really interested to send telescopes into space. So telescopes in space solve all these three problems. Location, technology can help overcome light pollution and turbulence, but nothing short of going to the space can solve the problems of atmospheric absorption of light. However, we can make some adjustments to our instruments, so or what we call it adaptive optics. So rapid changes in the mirror shapes can really help us. So this is without the adaptive optics. This is with the adaptive optics. So in other words, this is another example of the observation of Neptune. So with and without. You can kind of see how turbulence in the atmosphere affects our data. And then we have interferometry. So these techniques allow two or more small telescopes to work together to obtain a better angular resolution for a larger telescope. For example, this is a very large area, VLA, in New Mexico. So in other words, you have one single dish, 10 meters, for example, but then this is not enough. If you wanted to make bigger, you can kind of avoid making a very big telescope by connecting a bunch of smaller telescopes together, and can act as a better angular resolution for you. Okay, so this is the end of chapter 5, and that was the end of chapter 5 part 3. Let me know if you have any questions. All right, stay tuned for for chapter 6. All right, take care.